Hello everyone. Welcome to the lecture of reciprocal lattice. Now, reciprocal lattice is an important concept in any course of solid-state physics or it may be nanoelectronics. So, today my lecture is about reciprocal lattice, which is just the inverse of direct lattice in a three-dimensional crystal or two-dimensional crystal, or it might be one-dimensional crystal too. Now, to begin, reciprocal lattice. Now we know that a lattice is a periodic arrangement of atoms or molecules. It constitutes the 3D elements. Now let us take a two-dimensional case first for simplicity. Now these are the atoms or molecules arranged in a periodic fashion. Now if this is along y and this is x, then the Bravais lattices are along x. Let us suppose this is my A1 and along A2 y, this is my A2. Then the translational vector in two-dimensional space will be, suppose U1 A1 plus U2 A2. Now in a Bravais unit or unit lattice in a three-dimensional space, when the lattice is orthogonal in nature, that is all the axes are mutually perpendicular, might be like this. Suppose this is a cubic lattice, then this will be A2, this will be A1, and this will be, this particular direction will be my A3. And for a orthogonal case, these are all perpendiculars. Now, this is the direct lattice. That means it is in physical space. It is in physical space. That means it's actually there in existence. Okay. Now, the concept of reciprocal lattice is very important in case of diffraction and X-ray diffraction, any kind of diffraction or any kind of experiment where you want to find out what is happening in the Fourier space or what is happening in the wave vector space. Now, how does the concept came into picture? So, let us try to understand that. In a periodic lattice, the solution, the solution to Schrodinger wave equation, Schrodinger wave equation is given by Bloch's theorem. Bloch's theorem. In a periodic lattice. A periodic lattice is given by the fact that the wave vector will behave as psi of r plus r will be equal to psi of r, where r is the translational vector. Now Bloch's theorem, the answer to the Schrodinger wave equation is given in Bloch's theorem, which is written as psi of r is equal to uk of r e to the power I k dot r. We'll take the solution on its face value and not try to deduce it. So this is the psi of r is equal to ukr into e to the power ikr. Now this is periodic in nature, this periodic function. uk of r, periodicity is of the lattice, uk of r plus r is equal to uk of r. And this is, we know that this is a plane wave solution, plane wave. This is a plane wave. So uk of r plus r, so uk repeats after the distance of a translation vector in two-dimensional space. This is, it might be u1 a1 plus u2 a2, where u1 and u2 are integers. Okay, so this is uk of r and this is a plane wave. Now, so let us try to see what is the form of Bloch wave after a translation of a translation vector capital R. So psi of r plus r is equal to uk of r plus r. We are just putting r plus r in place of r. This is r plus r into e to the power I k into r plus r. We have just replaced r by r plus r. But we know this is periodic in nature, so this will be equal to uk of r into e to the power I k dot r into e to the power I k dot capital R. Now, this is your psi of r. So this is psi of r into e to the power I k dot r. Now see, in a periodic lattice, after the translation vector, the wave must repeat itself. So psi of r, we are expecting psi of r plus r will be equal to psi of r, but because it is a periodic lattice, what happens at r, that repeats at the translation vector after capital R. So if this is equation 1, let us put the Bloch wave solution as equation 1. This is equation 2 and this is equation 3. So from 2 and 3, we can say e to the power I k dot r is equal to 1. This is 4. See, the phase term e to the power I k dot r will be equal to unity. So let us see, analyze this thing. E to the power I of k dot r is equal to 1. Now this is a phase term, k dot r. K dot r is pure phase. It is a phase term. It is a phase term. So let us try to understand how the concept of reciprocal lattice is coming into picture. Now R is in direct space, direct lattice that we have already defined. So as this is phase, phase is independent of any kind of lattice vector. So K would be inverse of direct lattice. So this is reciprocal space. So K dot R will be a pure phase. So if R is phase, direct lattice, then K dot R will be in reciprocal space. That is something, if R is analogous to D, then K will be proportional to 1 by D. Now we have already defined R to be U1 A1 plus in three-dimensional U2 A2 plus U3 A3. A1, A2, A3 are the unit vectors along X, Y, and Z. Then let the corresponding value, so K will be also in three directions, X, Y, Z. Let's try to find out what the relationship will be. So let us suppose K is equal to L into B1 plus M into B2 plus N into B3. A1 AIs and B A1 A2 A3 L M N are all integers. So if this has to be retained, this has to be obtained with this kind of three-dimensional representation, then we propose that this could be a solution. That is, the reciprocal lattice vector B1 will be 2 pi into, in cyclical fashion, A2 cross A3 divided by A1 dot A2 cross A3. B2 will be 2 pi A3 cross in cyclic fashion 1 2 3 2 3 1 divided by A1 dot A2 cross A3, and B3 will be equal to 2 pi into A1 cross A2 divided by A1 dot A2 cross A3. Now see, A1 dot A2 cross A3, this is the volume of the rectangular parallelepiped. This is the volume of the rectangular parallelepiped. A1, A2, A3. This is the volume of this rectangular parallelepiped. Now see, now suppose this is your A1, this is A2, and this is A3. Then A2 cross A3, this is a scalar quantity, as this is volume, the denominator is scalar. Now what is A2 cross A3? A2 cross A3, now this is A2 and this is A3. This is A2 and this is A3. A2 cross A3 is perpendicular from the plane containing A2 and A3. And if this is a rectangular parallelepiped, this is along the direction of A1. This is along the direction of A1. So B1 is along the direction of A1 and it is proportional to 1 by A1. So B1 is proportional to 1 by A1 or twice pi by 1 actually, and it is along A1. It is along the direction of A1. B1 is proportional to 1 by A1 and it is along the direction of A1. So we do understand that the inverse relationship between the direct lattice and reciprocal lattice, that is, if direct lattice is A1, B1 will be inversely proportional to 1 by A1. And the direction will be along the same direction of A1, at least for a rectangular parallelepiped. If A1 and A2 are not orthogonal, the things will change a bit, but the basic concept is like that. Now, with the help of reciprocal lattice vectors, so these are the equations, please note it down, B1, B2 and B3. It goes in cyclic fashion. B1 is equal twice pi into A2 cross A3 divided by A1 dot A2 cross A3, where the denominator is the volume. So this is the relationship. Now it has got lot to do with the diffraction X-ray diffraction experiment, And reciprocal lattice gives the proper representation of the first order, second order, third order diffraction phenomena, which is also called Bragg's diffraction. Bragg's diffraction. So we'll come to know it in a later lecture. Okay, thanks for listening. Good day.